No, is it not recording?
Usually there is a red button when it records, but I don't see it.
Yeah, no, I clicked the start recording, but it's not doing it. Can someone else try?
Now it is recording, I think.
Ah, okay. Now it says stop recording. It's doing it. Okay. Okay. Thanks. It's still there, right? Okay. Okay. So there are voting between. First, we start about voting between two candidates, A and B, and any X in Z2 to the N, we interpret as a voting pattern where +1 means +1 is vote for A. Let's say we just fix A versus B, vote for A, and -1 is vote for B. And if we take a Boolean function, Boolean function means it takes values in -1, 1. It's a manner of combining the votes. To get a decision. So f of x equals +1 means A wins, and fx equal to -1 means B wins. Okay, so that's the meaning of this. So what is it that one wants to do? There is not much. I will get to the problem that we are interested in. But first, in this problem, there are a couple of small interesting things which are nice. So some Boolean functions, of course, we like the democracy, we like majority function, right? So that is what we take. If there are two candidates, you pick the person who gets the majority of votes. But any Boolean function is a possible way of making decision. And we mentioned the extreme other case, opposite of democracy, where f of x is x1, which means whatever one says goes. Okay, so that is the extreme other case. But here are some. So what are desirable f? So this is just some small things which are nice. I thought I'll just go over them. So as I said, everything in this I'm doing from the book of Ryan O'Donnell, Analysis of Boolean Functions. So here are some what are desirable, in this case, what are desirable properties of f. That's what one can ask. And there are two things that I would like to say, which will somehow say that okay, democracy is good. Okay, and just to put it roughly. Okay, so one is, so there are two things. So some desirable properties. So first one is there a question? Okay, so some desirable properties of f. Okay, so there are some properties that one can give. If so, if you take if everyone votes for candidate A, okay, so if f of then you should not choose the other candidate, right? So this would be a good property. And similarly, if everyone votes for, it's a very weak property. If everyone is, so this is called, then we say that, so here is the property, and we say f is unanimous. At least in the case where everyone agrees that they want a candidate, that decision should be the one that's accepted. So it's a very simple, desirable property, minimal. You would like such a voting pattern to have with the voting interpretation. Maybe it is slightly more. Is f is minus f of x. Okay, in a way, it's slightly better. I mean, so only can happen or exists only such a function possible only when. Anyway, this is the definition of a property. If n is even, you know that you well, okay, it may be there. So let's just say this. This is an odd function. That's all. So it means if everyone flips their vote, then the decision also flips. Makes sense, right? That's an odd. So we say f is odd. So there's what else is good? I mean, so monotone would be good, right? So meaning if xi less than equal to yi for all I, then f of x less than equal to f of y. So this is called monotone. See, everything is plus minus 1. So when we say xi less than equal to yi for all I, it means that in x, whoever votes for A will also vote for A in Y, right? I mean, so if xi is 1, yi is necessarily 1. But if xi is minus 1, yi could be plus 1. So it means that person by person, the voting is better for more for A, meaning it's not just that A gets more votes. It's not that. Each person uh, in X voting is more likely, I mean, not likely, I should say, if they vote for A in under X, they will also vote for A under Y. But some people may have changed their vote from B to A when going from X to Y. So certainly in such a situation, if fx is 1, fy should also be 1. This property is not anything more than saying that. So this property is nothing except that if fx equals 1, then fy equal to 1. If fx equals minus 1, fy can be 1 or minus 1. We can't say, I mean, this doesn't say anything. The only thing this is saying is that if fx is 1, fy should be 1. And here, that is kind of a desirable looking property. If people vote more towards, if they change votes towards A and nobody changes in the other direction, then the vote should also, overall decision should shift towards that. That's called monotone. And another very good property, it is the hardest maybe to be achieved in history, is the symmetry. Equals f of x pi of 1 for all x and for all pi in the symmetric group. Okay, so permutation, any permutation. So if you permute the votes, then the decision doesn't change. That means this is a voting system which doesn't care about the identities of people. Okay, so it doesn't matter who votes for whom. It's really the if the identities of people are permuted, then the voting decision is the same. So these are some desirable properties of voting. So is it okay? I mean, so here is a very nice fact. It's an easy fact. It is apparently called May's theorem. That if the only function, what function has these properties? Okay, let's talk about, say, majority function. Majority function. So example of, let's do an example. So let n be 2m plus 1, odd. So that majority can be defined. And m of x is majority of. That means if more of them are plus 1, then this is plus 1. If more of them are minus 1, then it is minus 1. So this one, what does it have? So let's say for majority, does it have unanimity? I mean, if everyone votes 1, it is 1, and if everyone, this is 2. Is it an odd function? Yes, n is odd here, So it's a well-defined thing. Majority is well-defined because n is odd here. And so if everyone flips, the decision goes the other way. Majority has this also. Is it monotone? Yes. If you convert some of the minus ones to plus ones, majority can only go up. And does it have symmetry? Sure. I mean, it's very obvious from that. So what else? What other function you might want to take? If you take something like dictator function. So this is a dictator function. So does it have unanimity? If everyone votes plus one, then the dictator also is voting plus one. So it is true. And if everyone is voting, so it means that if everyone agrees with the dictator, that they all the decision goes, right? So this is okay. Is it odd? If everyone flips, then the dictator also flips. So this is also true. Is it monotone? Yes. Again, if everyone, I mean, if xi is less than equal to yi, only what matters is x1 to y1, right? If x1 is less than equal to y1, it's just x1. That is the decision. So it is also this. What is lacking there is the symmetry property, because everyone is not treated equally. One person is special. So that's an example. So if you take something like recursive majority, which I will not recall definition of. You remember that what we do is we divide the whole population into, maybe the country is divided into states, states are divided into districts. And what we do is we take majority in each district to decide the vote for the district. And then we take majority of the districts among the districts in a state to get the vote of the state. And then we take the majority among states to get the vote of the whole thing. So it is actually not same as majority, because by how much the margin they win inside a district is not going to matter actually, as long as so it may, so recursive majority would have which of these properties? So I mean non-trivial recursive majority. Majority is also a recursive majority, but typical recursive majority would have unanimity would be fine, odd would be fine, and monotone would also be fine. It's again lacking in symmetry. It has a certain better symmetry than the dictator function, in that all people, if this district is the lowest level, then if you permute people in any district, then it's okay. So it's a smaller group of symmetry that is there. It doesn't have the full group of symmetry, whereas dictator function has no symmetry at all. This has a smaller group of symmetry, really. So anyway, this is just some basic functions. So what May's theorem says is that if you have a function which has these four properties, then it must be majority function. In fact, if it is odd, monotone, and symmetric, then n is odd and f is majority. So in that sense, the desirable properties, the majority function is the only one that satisfies these things. Okay. By the way, if you have odd, monotone, and symmetric, the unanimity is automatic actually. So if you have a function which is odd, then f of 1 and f of minus 1, they must be opposite of each other. But it's also monotone, and this one beats that. So this will be plus 1 and this will be minus 1. So unanimity is implied by the way. So these three, when you have all these three, even symmetry is not needed. Odd and monotone imply unanimous. That's why I did not put in the conditions. We don't need that. Odd plus monotone implies it is unanimous. Okay, so the proof is very simple actually. So okay, so what is it? So f is monotone and symmetric. So what you can do is, so so it's, yeah, so the proof is actually quite simple. So I say that f depends, f must be of the form. Okay, so first of all, because of so any x can be brought to the form where 1, 1, 1, I have all the ones first and then the minus ones. Okay, by a permutation. There are many permutations which do this, but any x will be after a permutation brought to this form, right? So let us say here there are k ones and n minus k minus ones. Now you see that but any two such vectors are comparable. So if I call this vector vk, then any vk is comparable to vl. Vk less than equal to vl if k less than equal to l, because vl means there will be more plus ones and then fewer minus ones, right? So this comparison is there. So if you use the symmetry, and the symmetry plus monotonicity implies that fx can depend only on the number of plus ones. Okay, number of plus ones, because it's symmetric. I mean, it is, you can bring it to the form vk, and then it has to be an increasing function of k. So what can it be? But it's a plus minus plus, and f is plus minus 1 valued. So what can it be? It has to be indicator of x1 plus up to xn greater than equal to t for some t. Right? I mean, it cannot be anything else. I mean, I said number of ones. X1 plus up to xn is actually number of ones minus number of minus ones. It's 2k minus n instead of k. So increasing function of k is same as increasing function of 2k minus 1. So it has to be of this form. Now we also say odd. Odd implies t has to be 0, because that's where I mean, so if you flip all the xi's, it has to flip. So t has to be 0, but also, and n must be odd. Otherwise, x1 plus up to xn can actually equal to 0 is possible. And in that case, we cannot, that doesn't flip the sign. Okay, so it is actually that 0 should be the midpoint here, and it should be unattainable. So what we get is, the conclusion is fx is actually the sign of x1 plus up to xn, and n odd, and which is actually the majority. That's what majority does. You just add all the votes, and if it's positive, it means more people voted +1, and if it's negative, more people voted -1. So this is so it's a very trivial, I mean, fairly trivial, but a nice and pleasant fact that properties which you may abstractly feel desirable are satisfied only by the majority function. Any questions, comments here? Okay, another nice property which
so that should be 2 times indicator minus 1, right?
Which one?
Symmetry plus monotony implies a plus minus 1 valued. So
right. F is for me plus minus 1 valued, so I should write it. Yeah, thanks. So f has to take this takes values 0 and 1. If I want it to take values 1 and minus 1, I should write like this minus 1. Okay, it's just, I mean, so if it was 0, 1 valued, it would be indicator x1 plus up to xn greater than equal to t. But what I want is the values to be 1 and minus 1. So I just transform it to 2 times that. And you're right. So then it is, yeah, I should have said it that way. Yeah. So Now it is clear. So what this function is from t onwards it is +1 and below t it is -1. Earlier I had written a function which was taking 0, 1 valued, and then the odd, I mean actually I just glossed over it because I wasn't thinking. So this is right. So this is +-1. So now you want this to be an odd function. So t better be 0, and also that value should not be attainable. So that is x1 plus x10 should not be 0. So that's all. Yeah, thanks. This is an important point. So this is actually 2 times sine. Oh no, now it's okay. So sine is okay. Now it's okay. So this is in fact the sine of x1 plus. So this is actually equal to the sine of any questions? Sorry for that small mistake. Any other questions? Okay.
Sine of that minus t.
Oh yeah, at this point, yeah. Okay, thanks. Yeah, this here there is a t also. So this is actually minus, but it is also slightly ambiguous what it means when where sine 0 is taken to be +1. That's what is meant here. Okay. Okay. Yeah. So this is the majority. So it's one way in which you get the majority function as the nice function. Any other questions? If not, I'll mention another property, which is actually a nice one also. Very simple, but quite nice. So apparently another criterion is a desirable property. Of f is to have more or as many as possible, I should say, maybe. Happy voters. Okay, so one way voting scheme, if you have comparing two schemes, one voting scheme can be said to be better than another if it leads to more happy voters. Okay, why when a voter is happy? A happy voter is one who agrees with the final decision. So, for example, if x is, let's say, plus minus, and let's say f of x for some Boolean function, it turns out that this is minus. Okay, so that means these voters are happy because they voted for the winning candidate, and these voters are not happy. So in this case, there are 3 unhappy voters and 2 happy voters. Okay, so more happy voters is better in some sense. I mean, so this is a criterion. That's all. You can accept or not, but this is a criterion that it should have more. But it depends very much on x, right? So we'll make assumption. So here is a statement, proposition. Assuming random voting. So when I say random voting, it is always each xi is ±1 with equal probability and independent. In other words, it is just that you pick out of z2 to the n one vector uniformly and you look at proportion. That's all. You can remove the probability language if you don't want. In this, you can take proportions of x in z2 to the n which have a certain property. Okay. So, but it's same as saying that each voter votes equally likely to either of the two candidates, and different voters don't talk to each other. They decide independently of each other. So coin tosses, n coin tosses are made to fair coin tosses are made to decide this. So whenever I say random voting, I will just mean this. Okay. So in probability, we are often careful to say what random means. I mean, there are many ways one can be random, but here this is the only sense in which I am going to use it. So assuming random voting, the statement is the expected number of happy voters is maximized by uniquely by the majority function. Okay, so among all Boolean functions, the majority function is the only one which, I mean, that's the unique maximizer for the expected number of happy voters. The happy voters depends on the particular x. Thus, the same, I mean, Boolean function, a different x, the number of happy voters is different. So this is the theorem. I hope the statement is clear. The proof is again a very trivial one actually, but nice. I mean, because it's the proposition, I mean, it's not to prove a theorem, but the proposition makes sense that you should have more happy voters, but the majority is the one that maximizes. Why is that? See, fx is, so f is any Boolean function, right? 2 minus 1, 1. So then take any Boolean function. So of course, then absolute value is less than equal to 1. So what it means is that if you look at any x into x1 plus up to xn, so this is less than equal to absolute value of x1 plus up to xn. Okay, equality if and only if fx has the same sign as x1 plus up to xn. Okay, fx has the same sign as, so here I am assuming n odd. Okay, let's take n to be odd. The statement is further. So fx is, so this is clear, right? Fx is at most 1. So fx into x1 plus up to xn is at most the absolute value of x1 up to xn. And for equality to hold, either, yeah, so this has to have the same sign as this. Otherwise, it's flipping the sign. Okay. So because of that, if you take expected value, is less than equal to expected value of absolute value of x1 plus up to xn. So what is this? This is sum over k equals 1 up to n, because expectation is linear. Expected value of fx times xk, k equals 1 up to n. So this is less than equal to, you see that this is, yeah, okay, it's less than equal to this. So this is all inequalities, and here the equality holds x by x if fx is the sign of that. Okay, for each. So this is actually what? I mean, what is fx into xk? Look at fx into xk plus 1 if kth voter is happy. And minus 1 if kth voter is not happy. Okay, so what is this? This is the 1 if kth order. So it's really indicator that kth order is happy minus indicator that it is he or she is not happy. So it's instead of 0, 1, it is this. So it's indicator. So this is actually expectation of 2h minus n, where h is the number of happy voters. So that's what this is. So the expected number of happy voters, it's basically proportional to, 2 times expected number of happy voters minus n, that's all. So that is less than equal to this. This side is exactly actually the same when f is majority. Okay, because an fx is this is f of x is the majority of x. Right? So if fx is always majority of x, then this is exactly fx into x1 plus up to xn. Right? So then this is actually, so we have shown that expected number of, so this is expected number of, you can cancel the minus n and 2. So expected number of happy voters under f is less than equal to expected number of happy voters under majority. And for equality to hold, you must have equality for every x. And that means there is only one choice, that f is the majority. Okay, so that is expected number of expectation h under f is less than equal to expectation of h under majority, and equality if and only if f is actually the majority function. So just a simple proof, but nice pleasant conclusion. That's all. Any questions here?
Where are you using that votes are equally likely, like equality half?
I see.
You don't need that. I think it's true even without that. And like you can make a much stronger statement than this. You don't need the half. You don't even need the independent. I think it's still true.
Oh, is it true? Okay, let me see. Did I not use that?
Minus n thing, how do we get without equally likely? I don't know, maybe I'm wrong, but the 2h minus n replacement.
Say it, please.
So from this line where we had expectation of fx at
Some function of age, some increasing function of age, right?
Sorry, I did not catch it. Can you repeat? Who was it? Abhishek, is it?
yeah, so this reduction that we have, that we can replace things by expectation of 2h minus n, doesn't that require equally likeliness?
No, this is just linearity of expectation. Fx into xk is just indicator that kth voter is happy minus indicator that he or she is unhappy. Right? So if you add that up, you just get 2h minus n, irrespective of whatever. So this is actually, okay, I didn't have to put the expectation inside here. I didn't even use that. I wrote it like this.
Yeah.
So, okay, so you are saying that you don't need, 1 second, something is a bit uniquely, okay, one is, okay, so at least the uniqueness part requires every xi to have positive probability, every x to have positive probability, because we don't need equality if that particular string x has 0 probability. Right, so the uniqueness requires that all x should have positive probability. But are you saying that it doesn't matter? It's suspicious.
No, uniqueness requires at least one to have positive probability.
No.
No. All x to have positive probability.
It requires it to be positive everywhere because you want fx to be this for all x. So you can only conclude that fx is equal to this if equality holds here. You can conclude fx equal to this for all x with positive probability. Right? So strict inequality can hold for x with 0 probability. So you want, if fx, you want this to be for all x, then you want this. Okay, so this is interesting. I didn't actually think, but you're saying that it doesn't require independence. It doesn't require anything.
I mean, like it makes sense, right? Like majority will make most people happy. That's just how it works. It doesn't. They don't need to have equal probability of voting or whatever.
Yeah, but so when you say that you are going for a random state, I mean, when you say majority has more happy voters, in what sense? I mean, x by x, or it's not true, right?
No, like if you do, if the voters vote randomly in any sort of way, like anything, then in expectation, I mean, like I'm not saying this like a rigorous statement, but it makes sense to think that in expectation, more will be happy if majority is given the
So
like.
yeah, but for a particular x, it can go the. I see, I see. So actually, true. I mean, so maybe I'm making some silly point actually. So yeah, so this was, you're right actually. So x by x, sorry, x by x it is 2. I mean, this whole thing is nonsense. Yeah, so you're right actually. So I do no need for all this actually. It is 2 x by x actually. Yeah. Actually, sorry. I mean, so you know this whole thing. You are quite right. It is quite clear that majority, but the uniqueness is what is, if you want to prove uniqueness, you do this maybe. So sorry, this is actually fairly nonsensical. Whatever I did is not necessary. It's okay. I mean, not okay, but too late. Yeah. Okay. So let me go on further to the real topic that I want to.
By the way, maybe I misunderstood. I thought the argument was basically correct, except that independence was not required. Like I thought it was a clean argument with that.
Okay, so that's all. That's true. Nothing was required. I mean, so what Chinmay pointed out, that if you look at x by x, by definition, majority is the what agrees with the decision, right? X by for every single x, you take any Boolean function, it cannot have more happy voters x by x than majority. I mean, that's what is the first line actually.
Sorry, h by x as in happy voters by x. Is that what you're saying?
No. Take any voting pattern, then this is true, right? So all the what Chinmay is saying is a correct point. I mean, not that there is anything logically wrong with this, it's just nonsense. You just take this first statement, that's all is needed, because the left side is number of happy voters under when voting pattern is x.
Correct.
Is x, and the right hand side is exactly the same when under majority, when voting pattern is x. So x by x it is 2. There is no need to put expectation and other things. It would be silly to do that actually. So yeah, you're right. So Chinmay, this is a good point, and it doesn't require any of those things. So x by x it is 2. Yeah, that's all. Yeah, so I didn't think clearly. Thanks for pointing this out. So now let me come to the real topic. Any other questions? Any other questions? Maybe I should have saved some time by skipping that. Okay, so 3 candidates. Okay, so now I come to the real problem. So suppose we have 3 candidates. So here I was trying to say about what is a desirable Boolean function and all that, but forget all that. So when we come to 3 candidates, the question is, how do you even decide? Okay, so we have 3 candidates now, n voters and 3 candidates. And n voters. How to decide? Okay, So it is often it's not clear. So for example, so if let's say, so let's say 3 voters and one, so voter 1 prefers A to B to C, and voter 2 prefers B to C to A, and voter 3 prefers C to A to B. Then what do you do? Who should get? Who wins? It's not clear, right? I mean, you cannot decide anything. It's a completely symmetric situation. Anything you say for in favor of A can be used in favor of B or in favor of C. So it's completely ambiguous situation. So, but is that so? What we will do is this is exactly this ambiguous situation that we want to see. But is it really something that is likely to happen or not? So that is what we want to understand. Okay, so one way of what I mean. So first of all, let's come to the scheme. So the scheme is the following. So this so in O'Donnell's book, he mentions somebody, some French. Probably not mathematician, must be something else. Condorcet. This is the scheme. Decide between conduct 3. I mean, so what is the way of deciding? Okay, so it says that conduct 3 two-way elections. Three pairwise elections. So in this case, A versus B, B versus C, and C versus A. Okay, so here what is the voting pattern? So let us say X1, X2, Xn are the votes. Okay, by the way, here when I write, the first candidate is always 1. 1 means A, minus 1 means B. Okay, for B versus C, let us say the voting is Y1, Y2, Yn. So here Yi equal to 1 means B and minus 1 means C. Okay, so always the first candidate is +1, second candidate is -1. That's how I write. And here, let's say Z1, Z2, Zn. So the proposed scheme is to conduct 3 pairwise elections and find a way to pool the results together. What is a way to pool the results together? Okay, so conduct 3 pairwise elections and then you decide, you apply a Boolean function f. Okay, so f of x is the decision. So which is +1 means A wins, -1 means B wins. And -1 means B wins. Similarly, here you will decide using your Boolean function, which could be majority function or it could be anything else also. F of x, f of y, f of z. Right, so this is how you decide. So now if you are in the happy situation, so here if A wins above B, and A wins against C, we say A is the Condorcet winner. See, you see that it is then it is very clear. So A wins against B, it can't happen for two. There can't be two Condorcet winners. So if A wins against both, okay. So if whoever wins two of the election, I mean both the elections they contest, wins. The other B and B versus C will only be used to order the B and C. Okay, so that's all that happens. So we say that A is a Condorcet winner, and that's the decision. So this is, and the decision will be that A wins. That's all. And that will be the decision. Is this scheme okay? So, but of course, it is conditional on that there is one person who wins against both the elections. So here there is a problem, you see. I mean, exactly in this, what happens in the A versus B election? So voter 1, voter 2, voter 3. In the A versus B election, voter 1 votes for A because prefers A to B. And voter 2 votes for B. And voter 3 votes for A. So whereas in B versus, so A wins. I mean, if we are using the majority function, A wins. In B versus C, here the first person was voting for B because B preferred to C, and here second person is also voting for B, third person is voting for C. So B wins. And then in C versus A, and by symmetry, you see that first person is voting for A, but the other two are voting for C, so C wins. So there is no Condorcet winner. Okay, so that is the problem. So that there may be no such winner at all. If there is an unambiguous winner, we have no problem. We can declare that person to be the winner. But this is what happens. So this is in the case of majority. So I'm using F is majority. Okay. So the question is, so can we use some other Boolean function or something and always get a Condorcet winner? So this is a nice theorem of Arrow. It's sometimes called Arrow's paradox or something. It is from the 60s. Apparently, he got some Nobel Prize for that prize in economics for work related to this. I mean, including this, which is a main point of it. So, first of all, we have to make an assumption. Okay, so if we are writing like this, here I gave preferences. Here I just gave votes. Okay, so one assumption that we will make, that is that individual voters, if individual voters themselves are not clear. Okay, so firstly, so there is a slight difference between the way of writing on this side and the way of writing on this side. Here I'm saying voter 1 has a preference of A to B to C. Here I'm not saying that. Here I'm saying that voter 1 votes for A, I mean X1, depending on in 3 elections I have the votes. So one, you see, there will be a complete nonsense. So here is an assumption. Okay, so you assume that xi, yi, zi is not equal to 1, 1, 1 and not equal to -1, -1, -1 for all I. So this assumption I make. Okay, we are using this symbols here. So because what does 1, 1, 1 means? Because if x1 equals y1 equal to z1 equal to 1 means voter 1 prefers A to B, B to C, and C to A. So voter 1 is itself unclear about how to vote for. I mean, it's not a consistent belief system that you prefer A to B and B to C and C to A. Makes no sense, right? So let's assume that individual voters don't have this type of foolishness. Okay, if the individual voter himself or herself has this type of thing, then it's meaningless. Similarly, if -1, -1, -1, it goes the other way. What you should check is every other thing is okay. So if you have 1, 1, -1, what does that mean? So there are 8 possible tuples, right? X1, Y1, Z1 can have 8 possible tuples. I am excluding 2 of them. Everything else is unambiguous preference, because what does this mean? This means that A is preferred to B, and this means that B is preferred to C, and this means that here it is C versus A. -1 means A is preferred to C. So overall, this is same as A is preferred to B is preferred to C. Okay, and similarly, if you have 1, -1, -1, it means A is preferred to B, and here C is preferred to B, because B versus C it's -1, and in C versus A it's -1, so A is preferred to C. So what does this mean? This means who is most preferred? A is preferred to C, is preferred to B. So you can check. I mean, these are all the possible cases. I mean, 2 pluses or 2 minuses. So you consider all other tuples are unambiguous order of preference. So it is like this. So we will assume that xi, yi, zi is not having this ambiguity. Is this okay? Is this assumption okay? Any questions about it? Okay, if not, so here is non-Arrow's theorem. And let me put the assumption that we will make randomness assumption. So second is we will in fact we assume that xi, yi, zi is uniformly, randomly picked from the other possible 6 voting patterns, which is equal. So those are the 6 permutations of possible. Okay, those correspond to 6 permutations. So from what? From -1, 1 cube, except these 2 unambiguous ambiguous ones, 1, 1, 1 and -1, -1, -1. Okay, these are the ambiguous ones, and everything else is okay. Okay, so this is what we assume. Yeah. So, and the theorem now says that okay, so let me actually, sorry. So this one, I mean, it depends on what you want to say. So let's say this is assumption A and this is assumption B. So assumption A has no randomness. We just assume that xi, yi, zi are not this. Okay. So Arrow's theorem says that under assumption A, if for some f, Boolean function f, we always have a Condorcet winner, that is for all x. For all x in z2 to the n, then f is actually a dictator or something like that. So f is either then fx equal to xk for all x, or fx could also be minus xk for all x. It's an anti-dictator for some k. So it's a dictator or anti-dictator, meaning there is a dictator, but whatever he says, the opposite goes. So
It's 1 o'clock.
so these are the only two possibilities. So if always you have a Condorcet winner, then this is true. Okay. And so I will, time is up. So I will actually do the proof. Sorry, I wasted time. Otherwise, I doing something incorrect. Otherwise, I could have gotten to the proof of this. But no problem. So we will prove this next time. And the way we will prove is that we will take assumption B and show that there will be a positive probability of not having a Condorcet winner. Okay, because then it will imply that there will be, or rather, so what the way of proof will be probabilistic. So we will do it. So what we will do is we will take assumption B, and under that we will prove that if f is not one of these functions, dictator or anti-dictator, then with positive probability there will be no Condorcet winner. Which means that, of course, there are configurations X for which there is no Condorcet winner. Okay, so but that probability statement is a stronger statement. Okay, I will stop here.